So section 3.6 is going to talk about rational functions. So a lot of times we use r of x to denote them. For rational functions, you can hear from the word ratio is part of rational functions. Ratio means one divided by another. It means fractions. So p of x divided by q of x, where p of x and q of x are each polynomials. Now, rational functions are everywhere, but let me just kind of show you a place where it came up for me over the weekend. I had to give a presentation at a conference. So we've talked a couple times about some things happening in space. There was the DART mission just recently, and then that was where they collided a spacecraft into an asteroid to try and change its trajectory. And as part of all this stuff, I ran across this interesting data. There's a lot more space junk out there. It becomes a big problem because these little pieces of stuff, you know, like there's a toothbrush or a wrench, are orbiting the planet at thousands of miles an hour. If you're in the International Space Station and all of a sudden this comes cruising by, that could ruin your day if somebody punches a hole in your ship. So they actually monitor this stuff to keep track of where it is at.
How does stuff get out there?
Well, you're fixing, say, like the Hubble Space Telescope, and you drop a bolt and it drifts away from you.
So it's
Now it's a deadly object.
Yeah, now it's something that we
You will pay for that mistake with your life.
or some of these things they fall apart, after a few years. So the number of objects has been growing and growing and growing. And I wanted to take a look at that, and it's kind of a nice jumping off point for us in terms of what we're going to look at today. So here's the data, and kind of at a first approach, you could say, oh, well, let's fit a line to that. And yeah, okay, it's not a bad line, but is this a good fit for the graph?
No.
No. So then my next approach was, oh, well, let's put an exponential function. Exponential functions are coming your way in chapter 4. So let's put an exponential function there. Okay, that looks better. Looks better. But then I'm like, you know what? We're actually going to be dealing with rational functions in this chapter. So let's do something for this chapter. And that looks pretty nice. That's a pretty good graph. It's a good fit to this set of data. And objectively, it's a little bit better than what we had just a minute ago. You can take a look back. Yeah, the exponential function is not bad, but the rational function is certainly better. So let's learn about rational functions. They're pretty useful. I think your graphing calculator probably uses rational functions, although Texas Instrument hasn't confided in me with what they do to come up with their numbers for you. In any case, let's look at rational functions and start understanding some things about them. We'll start with a very simple one. Y equals 1 over x minus 3. And let's make this a little darker. Now, there's a couple outstanding features about this graph. Certainly, there's a place where this graph has an issue, a problem. Can you see where that would be? Where is there something pretty interesting going on with this graph? Yeah, the asymptotes. And I like that you said plural because there's two of them. But one of them is where the denominator equals 0. Fact that x equals 3. And you've got what's called a vertical asymptote. The graph approaches but never quite touches this line. So maybe I should make that a dashed line, just to remind you that it's not really part of the graph. Now that's one asymptote, but is there another one? Yes, y equals 0, the x-axis. So y equals 0 is another asymptote for this graph. The graph eventually gets very, very close to, but never quite touches the x-axis. All right, so there's a couple asymptotes. We're going to be looking for the horizontal asymptotes, the vertical asymptotes, and there's going to be one more in this category called an oblique asymptote, or the book calls it a slant asymptote. We'll probably go with that pronunciation, but okay. Let's take it over to some of the examples here. So how about here? So it says, what are the asymptotes? And maybe I can give you a better look at that. Here, 3, 6. There we go. Let's just make that view a little bit bigger. So it says, what are the asymptotes? There's 2 of them. And please don't just give me a number when I ask you for the asymptotes. I'm going to want an equation. So let's see if we can't figure out what those equations are. How about for the vertical asymptote? What's the equation of that one?
X equals 2.
X equal 2. Perfect, thank you. So you got x equal 2. How about the horizontal asymptote? What's that one?
Y equals 2.
Y equals 2. Beautiful. And now we want to figure out what the end behaviors are. So the end behaviors are this. So as you're moving out the x-axis in the positive direction, what's happening to the y coordinate of your graph? So what's happening to your y value there? Where is it going?
It approaches 2.
It's approaching 2. Nice. Well said. You're ready for calculus.
Indeed.
He's like, yeah, I'm signing up tomorrow. All right, let's go out towards negative infinity. Now where's the y coordinate going to?
Approaches 2.
Same thing again. Approaches 2. So you get the same end behavior. They don't always have to have the same end behavior. Sometimes they can have different end behaviors. It's going to depend on the problem. Now, let's just do example C before we come back and cover example B. Are there any vertical asymptotes here for example C?
No.
No, there's not. So you might have to write D and E does not exist or something similar to that, but there's no vertical asymptotes there. How about some x-intercepts? Where are the x-intercepts?
4 and -4.
Thank you. 4 and -4. All right, so x equal 4, x equal -4, bless you. Is there a horizontal asymptote for this graph?
Y equals 2.
Yep, y equals 2. So right here, y equals 2. And again, I really appreciate you giving me an equation here. When I get 2 or 4 or 3 or something like that, it really gives me a tough time because I need to know that you know it's a horizontal line, y equals 2, as opposed to a vertical line, x equal 2. So, and last but not least, the y-intercept. -6, yeah. So I'll just list the point, 0, -6. Great. But now when it comes to vertical asymptotes, they're very predictable. We kind of already saw an example of one just a minute ago. This had a vertical asymptote at x equal 3. How do you think you can look at the denominator of a rational expression to determine where there's a vertical asymptote? What are you going to have to do in general?
Find where x equals 0.
Yes, we need to find where the denominator equals 0. So set the denominator equals 0. Yeah, the denominator equals 0. So that's going to be x plus 1 times 4x minus 12 equals 0. Let's see if we can't solve here. So here x plus 1 equals 0. Here 4x minus 12 equals 0. That's going to be x equal -1. Someone do this in their head. What does x equal?
3.
3. So there's your vertical asymptotes. X equal -1, x equal 3. 2 vertical asymptotes. Beautiful. Now, you don't have to worry about complex values for vertical asymptotes. If you had, say, x squared plus 4 or something like that in the denominator, it's not gonna have a vertical asymptote. X squared plus 4. When you set this equal to 0, you'd end up with two negative values or two complex values. You're not going to get imaginary asymptotes. They only count if they're real asymptotes. X-intercepts. For this, you're going to set the numerator equal 0. Set the numerator equal 0. Okay, let's do that. So,
Should you factor out an x first?
well, we will as we solve it. So it's going to be x squared plus x equals 0, which is x times x plus 1 equals 0. We have two solutions here. X equals 0 or x equal negative 1. So if you're to look at the graph, you should see the graph crossing the x-axis at these places. We're going to come back and work with the horizontal asymptote in just a minute. But before we do that, let's figure out what the or the y-intercepts are. In general, how do you find the y-intercepts?
Set x equal to 0.
Set x equal to 0. Perfect. Set x equals 0. Can anyone do that in their head with this particular problem? If I set x equal to 0 in this expression,
0.
yeah, you're going to end up with 0, right? Because you have 0 squared plus 0 divided by, whatever. It's still going to be 0. As long as you're not dividing by 0, you're fine. And if I put in a 0 here, I'll be dividing by negative 12. So 0 for x gives you 0 for y. So that leaves us with one last thing, and that is, what are the horizontal asymptotes? Well, those turn out to be actually predictable. And let's take a look at those. There's three different cases that you could deal with in terms of where you're going to get an asymptote. If the degree of the numerator is less than the degree of the denominator, then you're going to get y equals 0 as a horizontal asymptote. This is on that little sheet that I gave you just a minute ago. Well, actually at the start of class. This one. What else could happen? Well, you could have the degree of the numerator equal the degree of the denominator. And if that's the case, then y equals a over b is your horizontal asymptote, where a and b are coefficients of your numerator and denominator polynomials respectively. So it's just going to be the ratio of the leading coefficients. And finally, there's one more case that we're going to have to deal with, and that's a case where the degree of the numerator is one more than the degree of the denominator. So it's this one right here. And if that's the case, then you've got to divide this stuff out, and then the quotient, y equals the quotient, that's going to be the equation for your slant asymptote. Now, I have a different term for that. I like calling it the oblique asymptote. If your book wants to call it the slant asymptote, or if you want to call it the slant asymptote, that's fine. I'm fine with either one. Let's figure out what case we're working with for problem B here. Now, if you're to multiply x plus 1 times 4x minus 12, let's multiply out the denominator. That's going to be 4x squared minus 12 plus 4 gives me minus 8 minus 12. So that's the polynomial I have in the denominator. Right there. So realistically then, let's see, let's do this. My polynomial looks like this. Let's see, x squared plus x over 4x squared minus 8x minus 12. That's my rational polynomial. Which of those three cases that we just went through is represented here? C. No.
That's B.
It's B, right? Now, it's not written, but what's understood to be in front of the x squared? A 1. So that's going to help me out in terms of figuring out what the actual asymptote is going to be. It's going to be y equals 1 over 4. That's going to be your horizontal asymptote, because it's the ratio of the leading coefficients, and that's as far as you've got to look with it. That's it. You're done with that part. So, yay, done. Let's see that this matches our expectations in every way. We want to look at the graph. We want to make sure that it passes through -1 and 3 on the x-axis. Excuse me. No, it has these vertical asymptotes, -1 and 3 should be vertical asymptotes. It should pass through the x-axis at 0 and -1. Should have a horizontal asymptote of 1/4 and also go through the origin. All right, a lot of things to check. Now, when you're putting this into decimals, then what you should do is type out the numerator, y equals x squared plus x, and then you highlight this and then hit the division key, and it puts everything in the numerator. Finally, divided by 4x squared minus 8x minus 12. And let's shut off some of this other stuff here. There we go. Well, let's see, take a look here. We expected asymptotes at x equal -1. Oh, something's wrong. How come I'm not getting an asymptote? Oh, there's something more devious going on there. All right, we'll talk about that in a second. And then we do get one at x equal x equal +3. Let me shut this off for the second. And then we also get y equals 1/4. That's a vertical, horizontal asymptote. And that looks reasonable. All right. Let's get rid of the minor grid lines. There we go. So 2 of our asymptotes are okay, but one of them isn't checking out very well. And what's going on with that other one? And I probably should have looked at the graph a little bit more carefully before we did this. But here's what's going on with that top one. This is something you're going to see in your calculus class. So let's take a look at r of x equals x times x plus 1 over the denominator of x plus 1 times 4x minus 12. Now, as far as the domain of this graph is concerned, x can't equal -1 and x can't equal +3, because that would put a 0 in the denominator. But if you're avoiding that point, what does it look really tempting to do? Looks really tempting to cancel those things out, doesn't it? That's why we're not getting a vertical asymptote at -1, is because these terms effectively cancel each other out. So x over 4x minus 12. Interestingly enough, your graphing calculator will show this a little bit better than Desmos will. So right here, we'd have to kind of codify this and say x can't equal -1. This is not defined there because this isn't defined there. Other than that one point, these two functions are equivalent. Now I'll show you what happens with this just out of sake of completeness. It's not something you have to worry about in terms of an exam. But that function is just not defined at that point. Let's see here. Clear that out. So is x squared plus x squared plus x divided by 4x squared minus 8x minus 12. And I'm going to graph that, say, from, let's see, do -3 to 1 on the x-axis. And then I'll let my calculator do the rest of the work. Zoom 0. Notice something interesting that happens at -1. There's a hole in the graph, right? That's because the graph is literally undefined at that point. Desmos won't show you that hole, not without a lot of work. But there's a hole in that graph. Anyways, so that's a heads up for you guys when you get to calculus. You're going to see those kinds of things happening. It's called removable singularity, but that's going way beyond what we need to deal with right now. Let's keep going with some of the examples that are relevant to you in your future. That would bring us to example D. So this is kind of a nice one because it's a little bit of a review of what we just have covered. They ask you to find the vertical asymptotes and the horizontal asymptote. So a couple nice quick hitter type problems for us here. Let's start with, what do you want to start with? I guess the vertical asymptotes, right? In order to find those, Jen, what do I got to find? What do I got to do to find the vertical asymptotes in general? Yeah, perfectly. So set the denominator equals 0, so I want to find the vertical asymptotes. So set the denominator equal to 0. Okay, that's going to be 4x squared plus 10x minus 14 equals 0. That's looking kind of ugly at the moment. And if you're like me, when I took this class, I was terrible at factoring. Hattie's looking at that going, oh, I hate these. All right, and I don't blame you. All right, factoring these things is not fun. But what you can do to make your life a little bit easier, I think, Jess, you might be noticing that, is that you can factor out a common factor of a 2. Does that make your life a little bit easier? Actually, it does. 2x squared plus 5x minus 7. Okay. Now what about that 2 hanging out in front? Makes no difference whatsoever to the solution at all. If you don't like that 2 out in front, let's get rid of it. I'll divide both sides by 2. On the left-hand side, the 2's cancel. I'm left with 2x squared plus 5x minus 7. Somebody do the right-hand side without taking out their graphing calculator. Goose egg. So that constant that you factored out didn't make a difference to the solution at all. But now I need to factor this. And I know it's going to start out with a 2x and an x. That's kind of nice. What's also nice is that the number 7 doesn't have too many factors, right? the last two numbers here have to factor as a 1 and a 7 or a 7 and a 1. If I put the 7 on the outside, then the 2 is going to multiply the 7, and I'm going to get 14x. I don't think I'm going to come back to 5x that way. So let me put the 7 here, and that means a 1 here. 7 times 1, yeah, okay, line them up pretty good. I've got a 50-50 chance now. One of these has to be positive, one of them has to be negative. What are you thinking? Positive, negative, or negative, positive?
Negative.
Turns out to be positive, negative. Let's check it. 2x squared minus 2 and plus 7 gives me a plus 5, and the last term gives me, bingo, minus 7. So I got this times this equals 0. What are my two solutions then?
Negative 7 halves and 1.
Yep. So I got this times this equals 0. This means x minus 1 equals 0, or x equals 1. Here, 2x plus 7 equals 0, so x equals negative 7 halves. And that's your first two answers. Be careful if they say something goofy. I'm being really, really polite compared to how I feel. If they say something goofy like, list your answers in order of, smallest to largest. I really, really don't like that. I'm very unhappy with Web of Science for being like that, but that's the way it is. All right, so we got our vertical asymptote. Yay. How about your horizontal asymptote? Which case are we dealing with? We have the three cases. Is it the case of the degree of the numerator is less than the degree of the denominator? So y equals 0 is our solution.
Case B.
All right, case B, they're equal, so it'd be the ratio of the leading coefficients. And then there's case C, which is a lot more work. But fortunately, we won't have to worry about that until the very end of the section. Quotient. All right, so yeah, I think somebody volunteered the correct answer here. It's case B. So our horizontal asymptotes are just going to be the ratio of these leading coefficients. So the horizontal asymptote will be y equals what over what? 16 over 4. And I would greatly appreciate if on my exams you simplified that. So y equals 4. Whew. Nice. All right. We're going to skip example E. I'll make quick work of example F. And I think I want to look at example F on here. Example F refers to this graph. Let's see, can I go a little slower? The first thing they ask you for is the x-intercept. And the x and the y-intercepts are both the same. They pass through 0, 0. So 0, 0 is your answer for the first two. Vertical asymptotes. There's two of them. And here again, Web of Science a little bit kinder than I'll be on an exam. I'll just ask you for the vertical asymptotes. They kind of start you out with x equals. So in this case, it'd be x equal negative 2. Where's the other one?
5.
Thank you. 5. Horizontal asymptote. Not quite as clear here, but it does have a horizontal asymptote. What does it look like? Y equals 0. Identify the function. Well, that's why I started off the way I did, because it's not an exponential function. Quadratic functions, we know what those look like. And in as much as we're studying rational functions, that might be a good guess. Rational functions. Either way you go, as x approaches infinity or negative infinity, y approaches 0 both times. So, yay. Okay, that brings us down to example H. Where's the vertical asymptote here, for example, H? You've got x minus 7 in the denominator. Where's the vertical asymptote? X equals 7. Good. X equals 7. And that's already drawn for us here. X equals 7. But there's another strange line on our graph. Let's see if we can understand it. Where's the horizontal asymptote, or what case of the horizontal asymptote are we working with? Yeah, that one's C. So if it's case C, you've got to do some division. Now, fortunately, in this first example with division, it's pretty simple. You can use synthetic division. So if I use synthetic division, it's going to be 7. And then let's think about what I'm going to write underneath. There's a 1 and a 3. Beautiful. And a 0. Because that 0, even though it's not written, there's plus 0 there. We've got to account for. So add going down. 1, 7, 10, 70, 70. That's great. But what does all this mean? That means something here. What does it mean? Angel?
So it divides to x plus 10 with a remainder of 70 over x minus 7.
Perfect. This is your x plus 10. That's the quotient. And then this is the remainder. We don't need the remainder. Y equals x plus 10. That's your equation of your oblique asymptote, or your slant asymptote. And that goes in right here. Y equals x plus 10. Great. And you can get the rest of the graph off of Desmos or your graphing calculator. I don't care. I'm not really looking for you to give me, a hugely accurate looking graph. I just kind of want the general gist of it, which is going to be something like this. All right, there's your graph. It has these almost parabolic shapes into each little corner, and then they bounce out. So, let's see. You can actually plot a point or two if you want, just to make sure you've got a decent looking graph. But, something like that, and something like that. All right. Mostly what I want you to be able to get are the horizontal and oblique asymptotes. And I got to finish up with one last one, because it's going to be the hardest one for you on your homework. Now, I've already got it completely drawn for you. I'm hoping that you can see where the denominator equals 0. And that's going to be when 3x minus 3 equals 0 or x equals 1.
Did you write that in?
As far as the rest of this is concerned, can I figure this out with synthetic division? Minus x squared plus 4x over 3x minus 3. The answer is not without some manipulation, because there's a coefficient in front of the x term. It's not just x minus something or x plus something. So, okay.
Long division, right?
Yeah, we can use long division. Even long division gets a little bit ugly here. 3x minus 3 into minus x squared plus 4x plus 0. The good news is we only need the quotient. Bad news is we need the quotient. So let's look here. The first thing I got to do is I got to figure out, well, what do I multiply this by to get this? And for that, I'll do a little division. Yeah, negative x squared divided by 3x. That simplifies to negative 1 over 3 times x. And that's the term that goes up here. Negative 1/3 x. Yeesh. Fractions. It's all right. Fractions are numbers too. Let's multiply 1/3 x times this stuff out in front. Times 3x minus 3. And that gives me negative x squared plus x. So a lot going on there. And I get to subtract this. When you subtract, you're going to change the signs and add. So, okay, that becomes a plus, those will cancel, that becomes a minus, and then I'll get a 3x plus 0. And then this process starts again. Except this time it's going to be a little bit easier, and there's more good news. Remember I said all you have to figure out is the quotient. So let's compare this number and this number. 3x and 3x. 3x divided by 3x gives me 1. Guess what?
That's it.
I don't care about the remainder at all. All I want is the quotient. This is the quotient. Anything else is just giving me the remainder. So the good news is I can stop right here, and this much right up here at the top, y equals negative 1/3 x plus 1. That's your asymptote. Y equals negative 1/3 x plus 1.
That's so bad.
And that's it. I guess what worries me about this on your behalf is the fact that, you know, you got this fraction to deal with out in front. And it's just kind of a pain, it just happens. But like I said, the good news is that we didn't have to really finish it off. All right, sweet. Have a good one and see ya.